Hello, I am Dr. Puds, and today I want to talk about switches in electric circuits. I'm sure you are familiar with the concept of a switch. It is quite intuitive. We have used them since we were very young. And if you have a simple circuit with, say, a battery on the left-hand side, a switch in the circuit, and a light bulb on the right-hand side, we know what happens. If the switch is off, then the light bulb is off, and if the switch is in the closed position, if the switch is on, then the light bulb is on. But maybe it's not quite as obvious what happens in this circuit in terms of the current and voltages. And in order to find this out, I find it quite useful to redraw the circuit ever so slightly, and to put both the switch and the light bulb in a clearly series connection. So we redraw the same circuit. We can give it a bit more space, and we have the switch here and the light bulb here, and they are in a series connection. This is important for our analysis. So if the switch is open, say our battery is 12 volts, then we find 12 volt across the switch and no voltage across the light bulb, and there is no current flowing. So I here is 0. If we close the switch, and I'm just going to draw this in red here, so we make the connection there, the circuit changes, because now we know the light bulb goes on. That is our experience. But how does it happen in the circuit? First of all, we will get a current flowing here, and say this might be 100 milliamps. It depends on the light bulb. Obviously, we expect this 12 volt voltage to be across the light bulb, so we might say there are 12 volts across the light bulb. And it follows from Kirchhoff's voltage law that there is no voltage drop across the switch. And that is a definition of a switch that is closed. It is a connection, and there is no voltage drop across the switch. And that is really important. So we see a change in voltage across the switch and a corresponding change in voltage across the light bulb. And that is how the switch operates. Either lets the current through, in which case we have no voltage drop, or it stops the current at that point, in which case the voltage drops across the switch. And this is a very simple example. Maybe we want to try something slightly more complicated. And I'll start with a circuit with 4 resistors in it. So again, we have a 12 volt supply. And now we draw 4 resistors that are arranged in a grid like so. Here we are, 4 resistors, nice and simple circuit. And we give them different values. Say this one here is 2 ohm, and the one below is 2 ohm, whereas the one on the right hand side is 1 ohm and 3 ohm at the bottom. This circuit is quite easy to analyze. Because we have 2 resistors that are in series, so we know here if we look at the left hand side, we have a series resistance of 4 ohm. On the right hand side, it is exactly the same. It's again 4 ohm, the sum of 1 ohm plus 3 ohm. So we can calculate the current through here. We find that through each of these columns we have a current flow of 3 amps, and so the overall current is obviously 6 amps. And this all changes once we add a switch. And I add the switch in between the 2 resistors here and the other 2 resistors. So here we put a switch. As long as the switch is in the open position, it actually has no impact on the circuit whatsoever, because it does not make an electrical connection. So the circuit stays exactly as we analyzed it. But this changes the moment that we close the switch. So again, I'm going to do this in red. We close the switch, and you can see how the circuit changes. Now we have 2 resistors in parallel at the top and 2 resistors in parallel at the bottom. So our previous analysis is no longer applicable. Instead, we need to look at this as 2 parallel resistors in series to 2 parallel resistors. And the way to analyze that is, of course, to look at the inverses of the resistances. So for the top row here, we calculate 1/2 plus 1 over 1 is, of course, so that's 1/2, and 1 is 3/2. This is the inverse of the resistance. So out of this we calculate the resistance is 2/3 or 0.67 ohm for these two resistors in parallel. At the bottom we can do the same equation. So we do 1 over 2 plus 1 over 3, a half plus a third, which is of course 5/6. And the inverse of this is our resistance, so 1.2 ohm is the resistance of the bottom two resistors. If we add these together, because they are in series, we can find the total resistance is 1.87 ohm. And from that we can calculate our new current, which is 6.4 amp. So what we can see here is the current has changed, 6.4 amps. And there is more current flowing now through the circuit. That is because we have closed that switch, we have opened up another path for current to flow in the circuit, and therefore we've made it easier for current to flow through the circuit. So it is logical that we see an increase in current through the battery, an increase in power flowing through the circuit. The next question might be how much current is flowing through each individual resistor, and that is quite easy. You can divide that up by the resistances, but first you need to calculate, of course, the potential here at the connection point. So the potential here is the first thing you would need to calculate for a more sophisticated analysis of the circuit. And you can do that because it is a voltage divider. You have the two resistors here, and you can calculate the potential at that point. I hope that has shown you a little bit about how switches work, how they can affect how you analyze a circuit, and how you can deal with circuits that contain switches and try to interpret what kind of difference the switch makes. Thanks for watching, and please have a look at my other videos on YouTube.